Hi everyone, I am Salman Parvez. I am a faculty member in RIT Dubai, Rochester Institute of Technology Dubai, United Arab Emirates. And today I am going to talk about the wire arc additive manufacturing process. We'll be reviewing technological aspects, some mechanical properties, application, and the challenges involved. The presentation summary is related to the brief background, motivation involved, technological variants of Waam, the mechanical properties, trending applications, some defects and challenges, then at the end cost comparison and some future work with concludes. As far as the background of Waam process is concerned, manufacturing sector is adopting additive manufacturing based techniques due to their ability to manufacture complex near net shape functional parts. The advancements in additive manufacturing is not limited to the process level, but also different difficult to cut materials are also being printed with exceptional mechanical character. Waam process was introduced back in 1920s when Becker come up with an idea to use an electric arc with filler wires as a source of heat to deposit the materials. Then Waam process is suitable to manufacture large-scale metal parts, and this is in contrast to powder bed fusion systems, which are famous for smaller products but with high definition components. Also, Waam process is good for repair and maintenance operations for the components such as turbine blades as well as molds and dies. The motivation involved in this work is that it reduces the manufacturing time by 40 to 60% and the post-processing time by 15 to 20%, and at the same time it can produce highly complex geometries with very low cost. Also, in the literature, there is a lot of material available about the designing, utilization, in-situ online monitoring of process, in-situ quality metrology, and in-process control and sensing of the process. There is also several efforts made in the literature to study the development process, material quality, path design and programming, and the process modeling. But Waam is a highly promising technology, and there is still need to understand the structure-property relationship of various Waam fabricated workpieces and their associated defects. If we talk about the different technological variants of Waam process, so it comes in three basic configurations: metal inert gas-based welding process, TIG tungsten inert gas based process, and plasma arc welding based process. So if you talk about the first one, which is metal inert gas is based on the electric arc that provides the heat for the welding of the material, and the use of the direct current between the base metal and the electrode is used to create the electric arc. Generally, argon is used to provide the shielding. Electrode is melted to form liquid drops of the metal, and these drops condense to form the beads. Then these beads are deposited on the parent metal in layer by layer, and the part is fabricated. So this is the schematic illustration of the process. Similarly, if we talk about the tungsten inert gas is very similar to the MIG process, the previous one, but in this case, the electrode is not consumable, and it is generally made up of tungsten. So this is the only difference. The construction in the torch and the uh, electrode is different, and filler material has to be provided from the outside in this case. So the schematic illustration is here with the welding torch schematic illustration as well. If I talk about the last variant, that is plasma jet or plasma arc welding, in this case plasma jet is created by heating the orifice gas in the torch, and the plasma is initiated with the application of high frequency AC voltage on the inert gas in the chamber. The plasma jet is forced to come out of the torch orifice or nozzle and hit the workpiece material. This is very intense in terms of heat, and this is how the welding is achieved. The process allows high speed, deep penetration, and welding narrow spaces with a good arc stability. So this slide talks a brief comparison of the processes, and here you can see the different sort of deposition rates involved. So with the arc welding TIG, 1 to 2 kg per hour deposition rate is there. and if you talk about MIG, so it is 3 to 4 kg per hour, and this is the last one which is available in the plasma arc welding. Uh, Before we go to the mechanical properties, there is another thing that the deposition rates in this case is compared with different additive manufacturing processes, and here you can see that the deposition rate for uh, Waam process is much higher than the SLM and the LMD process, as shown in this graph. Then if we talk about the mechanical properties of different materials, so first if we discuss, for example, the titanium alloy. So for TI64, there are several studies, and these studies reveal that the fabricated TI64 material is relatively just like the wrought TI64 and is higher than the cast TI64. The fabricated TI64 also showed an isotropic nature with less strength and the greater elongation when it comes to the aluminum alloys. So aluminum alloys is famous that the Waam process have lesser mechanical properties in comparison to the machine samples from the billet materials. In order to gain maximum tensile strength, post-processing heat treatments are required on the fabricated samples that refine the internal structure, microstructure. Other reason in some other studies that reveal that 7000 series and 6000 series, they are not providing good results is because they have poor weldability, and because of this thing the process is not dealing with them. If we talk about the structural steels, for example, so there's a study that discussed the weld bead. They discussed the sample, and it divide basically the sample into three zones: the lower zone that is in contact with the substrate, a cold substrate, then the middle zone that is basically dealing with the layer by layer fabrication of weld bead, and then this is the upper zone that will be in contact with the air. So in that structural steel, the upper layer was exposed to the air that absorbs a high thermal shock, and that result in the smaller grain size as because of the result of the rapid cooling. So this can be seen here. And the smaller grain size is linked with the higher strength because of the presence of more grain boundaries. The middle zone was made up of ferrite. It was due to the low thermal shock and can be observed with the low value of the hardness and the strength of the material. In another study, the study was conducted where the sample was fabricated using stainless steel as shown here, and the sample were prepared in the longitudinal and the transverse direction. It has been seen that in the longitudinal direction, very similar properties to the base material were observed. And deeper analysis provided that the microstructure was comparatively finer in the longitudinal direction. Some trending applications of Waam process are available in the construction, marine, automotive sectors. So for example, in the construction sector, Waam process is used for the fabrication of pipe, flanges, plant constructions, etc. And in marine industry, shipbuilding is again one of the major field where some of the companies they are working. And for example, this impeller was fabricated using Waam, and it was successfully implemented. Similarly, there are automotive companies like PEX, and they're trying to build chases, automotive chases using Waam process. Some of the defects which are there in the Waam fabricated parts, so residual stresses are there. It's very difficult to get rid of these stresses, and they generally affect the fatigue life of the material. So for example, there's a study that shows that once the parts is fabricated, the internal stresses are redistributed when the clamps are removed, and there are lower stresses on the top than the one at the interface with the substrate, and as a result there is a bending moment involved in the fabricated sample. However, applying the plastic deformation using rolling operation can benefit the process. Similarly, the second effect is basically the porosity involved, which means tiny cavities are there. As a result, once the impurities are fed into the process, such as humidity or grease, so they result in the cavities. It can be avoided by controlling the shielding gas, increasing seals to reduce the gas leakages. Similarly, literature provides a cost comparison of Waam process with other processes such as EBM, direct metal laser sintering process and conventional CNC process. So it can be seen that when these two shapes were fabricated, the Waam process provided the lowest cost. In the end, some conclusions and some futuristic directions. So it has been observed that cooling curve plays an important role in the performance of the Waam samples because it controls the microstructure. When the cost comparison is performed, the Waam process outperformed other counter processes such as EBM and direct metal laser sintering process by 20 to 45 and 69 to 79% respectively. There is again need to further explore the finite element based approaches where multi-physics models can be engaged and Waam process can be simulated. Thank you for your attention. If you have any question, please go ahead. Thank you.